Learning Outcomes 7.2 and 7.3. Define the terms Nyquist rate, Nyquist frequency, and aliasing. Determine for a given signal the Nyquist rate, Nyquist frequency, and whether or not aliasing occurs. In the previous video, we showed how when we're doing impulse train sampling, we will wind up with a spectrum of our original signal that repeats itself, spaced at 0, omega s, it will continue 2 omega s, 3 omega s, negative omega s, negative 2 omega s, and that the amplitude will be scaled by 1 over t from what the original amplitude was. Review that video if you do not remember these details. The next question comes, where are these triangles with respect to each other? For that, we need to look at the values of the neighboring points. As long as omega m is to the left of omega s minus omega m, and thus omega m is less than omega s minus omega m, these triangles will not overlap. We can do that same calculation over here if you say negative omega s plus omega m is less than negative omega m. You'll get the same thing when you simplify. We can take this mathematical condition and do some algebra, and we come up with the equivalent statement that so long as 2 omega m is less than omega s, the triangles will not overlap. This condition is called Nyquist theorem. Sometimes it's referred to as the Nyquist criteria. 2 omega m happens also to be the total width of our non-zero spectrum in our signal. And remember that omega s is our sampling frequency, 2 pi over capital T. And capital T is how far apart we are doing our sampling in time. What if this is not the case? If we wind up with 2 omega m is bigger than omega s, the Nyquist criteria will not be satisfied, and we will wind up with omega m being to the right of omega s minus omega m. This means that our spectra overlap. We would have to then add the spectrum to get our final spectrum, and we call this aliasing. Aliasing is bad. It's something we do not want, because if we've done that, we no longer have the unique information about our signal in this frequency band. If we knew it was a triangle, we could back it out. But if we knew it was a triangle, we could just draw a triangle. Remember, a triangle is only trying to illustrate the general spectrum. The actual shape of your spectrum will not be a triangle and will generally be very rough, as you'll see in lab. Okay, let's look at this again. Let's assume we do not have aliasing and everything is nicely spaced. We're talking about a signal x of t that is real. Therefore, the magnitude will be an even signal, which says that what we have on the right will match what we have on the left if we mirror it around 0. Because we're taking our triangles up and moving them from one spot to the next spot through the sampling, what we have here for spectrum is the same spectrum that we have here. Therefore, we quite often in reality will look at the spectrum only in this band. If in lab you were to perform a fast Fourier transform, the spectrum is returned in this region. You can take this part of the spectrum from the middle to the end and pick it up and move it back over here because it repeats. And what you have here, you can pick up and move over here. From this one small portion of our spectrum, we know the entire spectrum from negative infinity to plus infinity. The spectrum for a sampled signal is periodic. Let's look a bit further. Omega S is the end of this viewing window. It's our sampling frequency, also called our Nyquist rate. The Nyquist rate is also called the sampling rate. The midpoint is omega S over 2. That's called the Nyquist frequency. These two names are very similar, and a lot of people mix them up, occasionally even in a textbook, and certainly quite often on the web. It's important that you know the two of them. You'll be asked this repeatedly in lab, and they provide a lot of information about what's happening during the sampling procedure. Something that's important to note is that if you're given omega m, you're given the maximum non-zero frequency component in your signal of interest, the signal you want to sample. You can determine the smallest value of omega s that satisfies the Nyquist theorem or Nyquist criterion. If you're given omega s, from there you can determine the largest value of omega m, the largest non-zero frequency you can have in your source signal, so that aliasing does not occur, and therefore the Nyquist theorem or Nyquist criterion are satisfied. If you're given both omega m and omega s takes precedence, and then you can determine whether or not aliasing will occur based on looking at the Nyquist criterion.